welcome back to part 2 of our biological chemistry lecture series. What I want to do first is just review briefly some of the concepts that we talked about in the last lecture. What we did in the last lecture was talk a little bit about elements and atoms, specifically that atoms were the smallest unit of matter that retain the properties of an element. We also discussed subatomic particles, and more importantly, how electrons and electron configuration play a role in chemical behavior. We then went on to discuss different types of bonds that can occur between atoms. We discussed the covalent bond, which was the sharing of a pair of valence electrons. We also discussed ionic bonds, that is the attraction of cations and anions due to electron transfer. These two types of bonds occur between atoms. We also then discussed the hydrogen bond, which is bonding that occurs between hydrogen atoms that are covalently bound to electronegative atoms. This type of bonding is a type of bond that occurs between molecules rather than between atoms. So this slide is really just to help us refresh our memories about the hydrogen bonding that we discussed at the end of the last lecture. Specifically, when you have bonds, covalent bonds that are polar covalent bonds within a molecule, such as what you see within water, you end up with a molecule that is considered polar. That means that portions of the molecule have an overall negative charge, and that's because the electrons in the covalent bond are not shared equally. They spend more time around one atom than the other. In water's case, that's what happens with oxygen. The electrons that are shared in the covalent bond between either hydrogen and oxygen spend more time around the oxygen atom, hence the oxygen portion of the molecule has an overall net negative charge, whereas the hydrogen portions of the water molecule have a net positive charge, again due to the fact that the electrons spend more time around the oxygen atom than they do around the hydrogen atoms. Because of this, you get a polar molecule, and with polar molecules, you can have interactions like we see here with hydrogen bonding, specifically occurring between molecules. So the net negative portion of one water molecule is attracted to the net positive portion of another water molecule. And so this feature of hydrogen bonding is going to be what's going to let us jump into the first topic for this lecture, which is discussing the importance of water. So the first part of today's lecture is going to be focused on water and the properties associated with water. Why is water so important? Well, it turns out that water is in fact essential for life, meaning that organisms cannot survive without the presence of water. In addition to that, about 3/4 of the Earth's surface is covered in water, so this plays a really big role in biological interactions, organisms with their environment. But more importantly for our cell biology class, one of the things to note is that about 70 to 95% of any given cell is made up of water. So again, since this is a cell biology class and we're going to be focusing on cells overall, it's really important to understand this very significant component or molecule that is found inside every single cell. Now, it's not a mistake that I started off with the first slide reviewing hydrogen bonding and the structure and polarity of water. It turns out that this feature or characteristic of the molecule known as water, the fact that it is polar and the fact that it has the ability to form these hydrogen bonds, give it some very unique properties that again are really important for life as we know it. And so we're going to continue on with those properties in the next series of slides. So as I mentioned in the last slide, all of the properties of water have to do with the fact that water is a polar molecule and can form hydrogen bonds. And it's these characteristics of the water molecule that again contribute to the distinct properties of water. The first two properties, like you see on this slide, are cohesion and adhesion, and they both are terms that sort of go hand in hand. They are distinct properties but are related to one another, so typically I like to talk about them together. Cohesion is a situation where hydrogen bonds hold a substance together. These are intermolecular interactions between like molecules. So cohesion is specifically the interaction of molecules that are the same due to hydrogen bonding. Because water forms those hydrogen bonds that we just reviewed, water molecules have the ability to interact with other water molecules, and this is the property of cohesion. Oftentimes, I sort of like to refer to this as water molecules sticking together. One example of cohesion or cohesive properties of water is what you see in the slide here. With water transport in plants, evaporation at the leaf is replaced with water coming in from the vessels down at the roots. So water transport in plants occurs from absorption of water at the roots and has to go all the way up in a tree, like you see here in this example, to the leaves. The way that water moves is because of cohesive properties. Another nice example that's not necessarily biologically related of cohesive properties of water is if you've ever taken water and maybe have a few drops on a table, you can see the droplet of water form, but if you push one drop of water towards the other, what typically happens is those water drops come together to make a larger water drop. And this is all due to the hydrogen bonding that's pulling those water molecules together. Adhesion, on the other hand, is intermolecular interactions between unlike molecules, molecules that are different from one another. This is described typically as the clinging of one substance to another. This is also sort of like a sticking, but in this situation, the sticking that's occurring is between molecules that are not the same. So cohesion, molecules that are the same, interacting with one another because of hydrogen bonding. Adhesion is going to be an interaction between molecules that are distinct from one another, but again, due to the hydrogen bonding. The example that you see here, again with the plant, utilizes adhesion as well. So not only does water stick together to allow for water transport to occur, but the water also sticks to the vessels that allows for the transport to take place. So both of these properties are really important in this example for water movement in a given plant. So cohesion, like molecules interacting with one another. Adhesion, unlike molecules or different molecules interacting together. Again, both due to hydrogen bonding. Okay, so next we'll move on to heat and temperature. Heat and temperature are related, but in fact are different concepts. Heat is the amount of energy associated with the movement of atoms and molecules in a body of matter, whereas temperature measures the intensity of that heat. Water can absorb and store large amounts of heat while only changing a few degrees in temperature. So, for example, when water is heated, heat, which is a form of energy, first disrupts hydrogen bonds. Then water molecules begin to move faster. Because the hydrogen bonds break first, water can absorb a lot of heat before the temperature goes up. So water is really good at moderating temperatures because of this feature or characteristic. So related to that then is the concept of evaporative cooling. When a substance evaporates, that means goes from a liquid to a gas, this is a change in physical state, the surface of the liquid remaining behind cools. So the surface where the liquid has remained is cooler overall after evaporation takes place. On a global scale, because there's so much water on Earth, this plays a really big role in cooling behaviors in regions that are closer to the ocean. At the organismal level, this is really important because it prevents overheating. So again, globally, what typically happens near very large bodies of water is that you have a more moderate or level temperature occurring compared to places that are inland where there can be dramatic changes in the temperature overall. This is something that maybe you visualized or felt yourself in the summertime. It can be 110 here in Bakersfield because we're relatively inland. However, if you drive out to Pismo, for example, it may be 65 degrees. And so that change in the temperature, or that moderate temperature near the coast, is due to the absorption of all of that heat energy and results in very subtle changes in temperature close to the coast. Again, at the organismal level, this plays a really big role in not allowing organisms to overheat and regulating temperatures within the organism. Another property of water is surface tension. Surface tension is the measure of how difficult it is to stretch or break the surface of a liquid. And here too, what you see is a great example with the spider sitting on top of a body of water. It seems as though the spider is not breaking through the water and is sort of floating on top of the water, but you can really see those imprints or depressions in the water from the spider overall. Hydrogen bonds give water an unusually high surface tension, which again does play a role in situations like you see here. So now we're going to switch gears just a little bit, still discussing the importance of water, but move on to a concept we might know as water being considered the solvent of life. Now, in order to discuss this characteristic or this property, what we need to do is define a few things. The first thing I want to define is a solution. A solution in chemical terms is a liquid that is a complete homogeneous or homogeneous mixture of two or more substances. Homogeneous just refers to perfectly uniform in composition. So when you have a solution, you have a liquid that is a complete, perfectly uniform in composition mixture of two or more substances. A classic example of this might be taking a sugar cube and putting it in a glass of water. Eventually, if you stir it a little bit, the sugar cube will form a uniform mixture. The sugar cube will dissolve and form a uniform mixture of sugar and water, where you cannot visually distinguish the sugar from the water. This is considered a solution. Now, in addition to those terms, we're going to add that of the solvent and the solute. The solvent is the dissolving agent of a solution. So in our last example, the solvent was in fact water. The solute is the substance that's being dissolved. And so again, in the previous example, the substance being dissolved is sugar, hence it would be referred to as the solute. We can also add one more set of terms, that is an aqueous solution. And this is what's relevant to talking about water here and water's importance for life. An aqueous solution is where water is in fact the solvent. So why is water considered the solvent of life? This goes back to the polar nature of the water molecule, again, meaning that there is net negative and net positive charges for every single water molecule. Because the water molecule is polar, it allows for water to interact very easily or readily with other components, substances, or molecules that also have positive and negative charges associated with them. So in the lower left-hand corner, you see an example in this case of sodium chloride, which again, sodium chloride is formed because of ionic bonds, which are interactions between positive and negative charges. But in this figure, you see some salt or sodium chloride being put in the glass of water. What allows for salt to dissolve is the interaction between the polar water molecules and the positive and negative charges in the sodium and the chlorine. If you look at the figure in a lot more detail, more specifically, if you look at the chlorine ion, the one that is negatively charged, it is surrounded by water molecules, but the orientation of the water molecules is specific Because chlorine has a net negative charge, chloride has a net negative charge, what you see is the water molecules interacting with the net positive portion of the water molecules, again, where the hydrogens are located, interacting with the negatively charged chlorine ion. The opposite is true for the sodium ion. The sodium ion has a positive charge associated with it, and the water molecules that are interacting with sodium have, again, a specific orientation, and that is the oxygen portion, the net negative portion of the water molecules, are what are interacting with the positively charged sodium. So in both of these examples, the sodium and the chlorine ion, you see differences in the way that water interacts. But specifically here, why water, again, in this case, acts as a really good solvent is its ability to interact with other positive and negative charges. So again, because of water's polar nature, water can readily form hydrogen bonds with charged components, as well as those that have polar covalent bonds associated with them. Now, water is not considered universal, meaning that it's a solvent for absolutely every type of solute, but it is very versatile because of this feature. In the right-hand figure, what you're looking at in the purple is meant to represent a large structural protein. And in this case, you do see water molecules interacting with the protein as well. We haven't yet talked about proteins and protein structure yet. We will eventually in our next series of lectures. But the important thing is that portions of proteins also have positive and negative charges. And it is because of those positive and negative charges, these portions of the protein, that allow for water molecules to interact with them. At this point, I want to add two new terms, and that is terms that describe or define how, in fact, other molecules interact with water. The term hydrophilic literally translates to water-loving. Hydro referring to water, and philic from the Latin filius, which means to love. So hydrophilic molecules or substances are water-loving molecules. They are substances that have an affinity for water. Specifically, these are going to be molecules or compounds that are dominated by either ionic or polar covalent bonds. These can be things that are also relatively large or too large to dissolve. So, for example, your cotton towel. The cotton fibers and the towel itself is extremely hydrophilic. This is why it does such a good job in absorbing the water off of your body after you've taken a bath or a shower. However, the towel itself does not dissolve in the water, it just absorbs the water. So I just wanted to differentiate that something that is hydrophilic doesn't necessarily mean that it will always dissolve in water, it just means that it has a nice, strong interaction or affinity for water. The opposite of that would be molecules or substances that are considered hydrophobic. Here too, the literal translation, hydro referring to water, and phobic from the Latin phobia means to fear. So these are water-fearing molecules. These are substances that do not have an affinity for water. These again are things that are dominated by non-ionic interactions and non-polar covalent bonds. Classic example of something or molecules that are hydrophobic are oils. So, for example, if you make a salad dressing, you put your vinegar and you put your oil and you put your salad dressing packet and you mix the two together. However, what happens over a short period of time, once you let that sit, is that there's a clear separation between the vinegar and the oil. That is because the oil itself is dominated by non-polar covalent bonds. It makes it so that it does not interact readily with water, hence the separation of the vinegar and the oil in your salad dressing. Focusing now on the figure in the center of the slide, there are occasionally situations where there are shifts in the hydrogen ion that occurs when water molecules interact. So on the left-hand side, you see the classic hydrogen bonding that would occur between two water molecules. However, in some circumstances or situations, one of the hydrogens can actually shift from one of the water molecules and become associated with the other. And this is what you see on the right-hand side of that particular figure. This results in something known as the hydronium ion and the hydroxide ion. And these again are ions because they do in fact have positive or negative charges associated with them. It is rare for this to happen, but it is important. Because of this dissociation event that can occur, like we've just talked about, this allows for situations where in the equation below is a little more realistic view. You have water dissociating to form hydrogen ions and hydroxide ions. And it is this dissociation that can allow for differences in behaviors of solutions to occur. And that leads us to talk about acids and bases. It turns out that the hydrogen ion and the hydroxide ion are extremely reactive. Changes in their concentration can drastically affect molecules in a given cell. So that leads me then to talk about acids and bases from the purely biological point of view. In chemistry, you may have had a slightly different definition, but for the biological definition, an acid is a substance that increases the hydrogen ion concentration of a solution. And the hydrogen ion is noted on this slide as the hydrogen with the positive charge associated with it. An example of this would be hydrochloric acid. In hydrochloric acid, when it is exposed to water, the hydrogen dissociates from the chlorine to produce hydrogen ions and chlorine ions. And in this case, the hydrochloric acid is acting as an acid because it is increasing the hydrogen ion concentration in the solution that it's in. The contrary to that is a base. A base is a substance that reduces the hydrogen ion concentration of a solution. Basically, it's a molecule that can accept hydrogen ions. One classic example is ammonia, which is NH3. And ammonia has the ability to accept hydrogen ions, become NH4+, and this is now referred to as ammonium. Related to the topic of acids and bases is the pH scale. pH is a measure of how acidic or basic a solution is. The range goes from 0 to 14, with 7 being neutral. A pH of less than 7 indicates acidity, whereas a solution with a pH greater than 7 indicates a base. pH is really a measure of the relative concentration of the hydrogen ion concentration and the hydroxyl ion concentration of the solution. When comparing solutions, a solution with a higher or greater hydrogen ion concentration would be more acidic, whereas a solution with a lower hydrogen ion concentration would be considered more basic. Now, concentrations of hydrogen ions and hydroxide ions in a solution can vary dramatically, and this is why scientists adopted the pH scale, which is a logarithmic scale of hydrogen ion concentration. And as you can see from the equation here in this figure or in this slide, pH is equivalent to the negative log base 10 of hydrogen ion concentration. So the example immediately below that equation is one that indicates a pH of 7. A solution with a hydrogen ion concentration of 0.00000001 molar hydrogen ions, or if we rewrote that as 1 times 10 to the negative 7 molar hydrogen ion concentration, would have a pH of 7. So, for example, a solution with a hydrogen ion concentration of 0.001 molar, or 1 times 10 to the negative 3 molar, would have a pH of 3. Now, the last thing that I want to say with this particular slide is that in addition to dealing with pH, we have to introduce one more concept, and that is of a buffer. Buffers minimize change in hydrogen ion concentration and hydroxide ion concentration by accepting hydrogen ions or donating them as needed. Basically, what a buffer does is maintain pH values at a constant level. And this is really important for biological function because variations in these hydrogen ion concentration can cause lots of problems overall for molecules and cells that need those molecules to function. The final topic for this particular lecture, dealing with a background to biological chemistry, is to begin discussion of how we build biologically relevant molecules. And in order to do that, we have to talk a little bit more about the atom carbon and how it plays a role in allowing for skeletons or framework of molecules to be built, which will then lead to biologically relevant molecules. So carbon itself is in fact a versatile atom, and we talked a little bit about this in the previous lecture. Carbon has the ability to form large, complex, and diverse molecules necessary for life's function. Organic compounds are oftentimes just simply referred to as molecules that are carbon-based. If you look at the figure here, what you see is something that we looked at when we discussed covalent bonds in a very simple molecular structure. In this case, we have a molecule known as methane. This is a molecule that is made up of one carbon atom and 4 hydrogen atoms. Carbon, again, has the ability to form up to 4 covalent bonds, and it's this characteristic, that electron configuration that we spent so much time talking about in the last lecture for carbon, is extremely important for allowing interactions to take place with other atoms. What we will do is begin by talking about carbon skeletons. And in this case, what we have on this figure are lots of different types of molecules that all are based on carbon and hydrogen. These molecules are referred to as hydrocarbons, and I'll refer to them or review them in the next slide in just a minute. Hydrocarbons, again, are just molecules that consist mainly of carbon and hydrogen. But for our purposes, this is really important because it allows us to add variation into a skeleton or a backbone molecule that will eventually lead to biologically relevant molecules. The first way we can build a carbon skeleton is just to allow variations in length, like you see in the top panel. In the top panel, we have a 2 carbon-based molecule. If we add one more carbon, we now have a 3 carbon-based molecule, and we can do this continually to add variation to the skeleton or the backbone molecule by simply just changing the length of the carbon skeleton. In the second panel down, what you see is another variation. This is a variation where the position of a covalent bond with a carbon is in a different location. These 2 molecules in the second panel down are made up of 4 carbons and 10 hydrogens. They both have 4 carbons and 10 hydrogens, but you can see that the arrangement of these components are different in the 2 molecules, and these are in fact distinct molecules. Even though the makeup is the same, the organization of those atoms in the molecule is in fact different. The third panel down shows you yet another way we can have variations in the carbon backbone or carbon skeleton, and this is with double covalent bonds. Double covalent bonds can in fact exist between neighboring carbons in a carbon skeleton molecule, but in this panel what you see is the position of that double covalent bond is in a different location. This adds different chemical behavior and as well as structure to the molecules in question, so the placement of double covalent bonds allows for variations to occur as well. Lastly, for biologically relevant molecules, certain hydrocarbon backbones or skeletons can form ring-like structures like you see here. And again, we will come back to that concept as we continue on with some of our future lectures. As mentioned on the previous slide, hydrocarbons are a family of molecules that are composed mostly of hydrogen and carbon. Typically, larger hydrocarbons are great sources of fuel for engines, and hydrocarbons can act as fat molecules for fuel for our bodies. What you see in this slide are two different examples of hydrocarbons. Obviously, the one on the left would be for fueling an engine. The one on the right would be for fueling our bodies. What you see, though, overall, again, is the long stretch of hydrogen and carbon in these hydrocarbon molecules. Now, alone, hydrocarbons typically are not biologically relevant molecules, but we can, again, add additional components to make biologically relevant molecules, which we'll get to in just a minute. Now, on the previous slide, one of the things I mentioned was the fact that you can change the branching position of where carbons are located. In that example on that slide, I mentioned that the molecule in question had 4 carbons and 10 hydrogens. If you look at the top panel of this particular figure, you see the exact same structure. These molecules are referred to as being isomers. Isomers are compounds with the exact same molecular formula, but different structures. So the first example of an isomer is categorized as a structural isomer, and structural isomers differ in their covalent arrangement. So in panel A, again, you see 2 molecules, both with the molecular formula C4H10. The one on the left-hand side with the straight arrangement of carbons, one right after the other in a chain, is a molecule known as butane. The molecule on the right in panel A is a molecule known as isobutane, and this again has a different branching pattern for where the carbons are located. Structurally, these molecules are different and do in fact behave differently from one another chemically. The next category of isomer is referred to as a geometric isomer, and that's what you see in panel B. Geometric isomers differ in their spatial arrangement. So in this panel, panel B, you can see a 2-carbon molecule with a double covalent bond between the carbons. The arrangement of where the hydrogens are located with respect to X, which could just be any additional component, is in a different location. So the molecule on the left, you can see the hydrogens are sort of along the bottom, whereas the additional X component is across the top. In the right-hand molecule, the X's and the hydrogens, both respectively, are on opposite sides of the double covalent bond. This does allow for different chemical and behaviors for these molecules. The last category of isomer I want to talk about is something known as an enantiomer. An enantiomer is going to be a molecule or molecules that are mirror images of one another, but the mirror images result in different shapes. If you look at the right-hand side, panel C, you can see an example of that. Your 2 hands are in fact mirror images of one another. However, if you try to superimpose them one on top of the other, the structures would be different. The shapes would be different. Your left hand is different from your right hand, even though it has all of the same components. And this would be what would apply to an enantiomer as far as molecular structure is concerned as well. So again, enantiomers are typically mirror images of one another, and this does oftentimes result in different types of shapes, which again gives different chemical behaviors to the molecules in question. The most classic example of this enantiomer would be in the late 50s with a drug known as thalidomide. The drug known as thalidomide was prescribed to pregnant women to help with their nausea in the early stages of pregnancy. However, when the drug was manufactured, both mirror images were formed or synthesized in the manufacture. One form was biologically relevant and did in fact help these women with their nausea symptoms. Unfortunately, the other form caused developmental defects, and there is a whole group of individuals that were born during this time that are referred to as thalidomide babies, and they have some extreme developmental defects due to the additional enantiomer form of the molecule in question. Now, what we've just done with the last several slides is discuss hydrocarbons, the carbon backbone skeleton to biologically relevant molecules. But what we want to do now is talk about how we actually build a biologically relevant molecule. Because again, for the most part, hydrocarbons themselves are not typically molecules found alone or in a significant concentration inside a living cell. So in order to build biologically relevant molecules, what we need to do is add components that are referred to as functional groups. And what we will do as we continue on with the next two slides is look at a whole host of functional groups that can be added on to a hydrocarbon skeleton to in fact build those biologically relevant molecules. 4 common ones are listed on this particular slide, and we will highlight them again in the next slide. Oftentimes I get asked by students, do we need to know the functional groups? And my answer to that is absolutely yes. You need to understand what the functional group is, what chemical characteristics it gives to the molecules, because this is what's important, again, as we get into those biologically relevant molecules. So this slide and the next slide highlights the 6 main functional groups that are commonly attached to hydrocarbon skeletons, again, to build biologically relevant molecules. So what we're going to do is go down these common groups, talk a little bit about them, their molecular structure, as well as the chemical attributes they give to the molecules they've been added onto. The first functional group is the amino group. The amino group is indicated by N, nitrogen, and 2 hydrogens. So if you look at the second column after the name of the functional group, you can see the structural formula of how this particular functional group would look. The letter R in any of the cases that we're going to talk about here next just represents the rest of the molecule in question. So highlighted in the blue is the actual functional group, which is NH2. The family of molecules that these functional groups are referred to as amines. And oftentimes you can find the amino group in a non-ionized form, like the formula you see before you, or you can find it in an ionized form that would look very similar to the next column where you've got the properties of the functional group. This particular functional group can in fact act as a base, and the definition of a base again is to reduce the hydrogen ion concentration of a solution. So this functional group can accept hydrogen ions from a solution, therefore making it act as a base. An example you can see in the far right-hand corner is an amino acid known as glycine with the amino group highlighted for you. In the center of this table is the next group down, known as the carbonyl. The carbonyl is actually found in 2 distinct forms. It is identified with a carbon and a double covalent bond to an oxygen. But the 2 categories of carbonyls are listed in this section of the table for you as well. There are those molecules referred to as aldehydes, and the aldehydes are going to have the carbon with the double covalent bond to the oxygen on the very end of a molecule, whereas ketones are types of molecules or family of molecules that again have the carbonyl group, the carbon with the double covalent bond to the oxygen, but that is somewhere internal in the molecular structure. So if the carbonyl is located on the end, it would look something like the molecule or the component that you see in the second column next to aldehydes. And then if it was somewhere internal in the structure, it would look somewhat like what you see next to ketones. So it's the placement of the carbon with the double covalent bond to the oxygen that dictates whether a molecule family will be known as an aldehyde or a ketone. And on the far right, you have some examples of those so that you can see acetaldehyde with the carbonyl at the very end versus acetone with the carbonyl sort of in the center of the molecule. The last functional group on this slide is the carbonyl. The carbonyl is indicated with a carbon, 2 oxygens, and a hydrogen. With the carbonyl, you can see the molecular structure, the carboxyl, you can see the molecular structure in the formula column. Again, this is denoted on the end of a molecule with a carbon, double covalent bond to an oxygen, and then an OH in the other covalent position for the carbon. The family of molecules that have this functional group are known as carboxylic acids, and they, as their title implies, do act as acids, which means that as an acid, they can increase the hydrogen ion concentration of a solution, and the way that they would do that would be to donate or release a hydrogen ion from the carboxyl structure. So in the properties column, you can see what the molecule or the functional group would look like once it has donated a hydrogen ion to the solution. So this is the ionized form of the carboxyl group. In the far right, again, you can see an example of a molecule that has the carboxyl group. This is acetic acid. So just to recap for this particular slide, we have the amino group, whose functional group can act as a base. We have the carboxyl group, which is a functional group that can act as an acid. Next, we have the hydroxyl group as a functional group. The formula is indicated with an oxygen and a hydrogen. The family of molecules that contain this particular functional group is referred to as an alcohol or alcohols. The properties associated with this is that this particular functional group is highly polar, so it makes compounds more soluble through hydrogen bonding with water. It may also act as a weak acid to release or donate a proton. In the far right, you can see an example of ethanol, which is a type of alcohol. The functional group in the center of this table is the phosphate group. The phosphate group is a little more complicated functional group in that it consists of 1 phosphorus atom and 4 oxygen atoms. And what you see in this particular state is in fact an ionized form. Biologically, this is the way you would find this particular functional group. The family of molecules are referred to as organic phosphates, and this particular functional group is going to become really important when we talk about energy and energy release. So for now, we probably won't talk about phosphate groups too much. We will come back to them probably when we get to Unit 2's material and Unit 3's material overall. But this is, again, a very important functional group. It does have biological relevance overall. The last group is the sulfhydryl group, and the sulfhydryl group contains sulfur and hydrogen. The family of molecules are referred to as thiols, and this particular functional group is really important for protein structure. Again, we haven't discussed proteins at all, which we will in our next series of lectures, and we will come back to the sulfhydryl group and how important it is for protein structure overall. And that's why we include it here in this list, because it does add to biologically relevant molecules. What we will do in our next series of lectures is do exactly that. Look at biologically relevant molecules, their chemical behavior, and their importance overall in cellular function.